De Havilland Trident. This was one of the first airliners built specifically around a deep, fundamental design compromise, and it very nearly reshaped how every T-tail aircraft afterward was designed. Introduced in the early 1960s, the Trident placed its horizontal tail high atop the vertical fin, well clear of engine exhaust and wing turbulence in normal flight. A layout that also let engineers mount all three engines cleanly at the rear of the fuselage instead of hanging them under the wings. But that same layout created a hidden trap. At a high angle of attack, the wing's own turbulent wake could wash directly over the tail, blanking it out almost entirely and stripping away the pilot's ability to push the nose back down. Engineers called it deep stall, a condition where the aircraft could pitch up, lose the tail's authority, and settle into a stable, unrecoverable descent. Nose high, engines often still running, controls doing almost nothing, the aircraft essentially falling flat out of the sky, with the crew unable to do anything about it. To prevent it, the Trident was fitted with a stick pusher, a system that automatically shoved the control column forward the instant a stall was detected, overriding the pilot before deep stall could even begin. In June 1972, a Trident took off out of London with a stick pusher that had been intentionally isolated, switched off following an earlier false warning during a previous flight. Minutes after takeoff, the aircraft stalled. The pusher never intervened, and the aircraft entered exactly the deep stall it was designed to prevent. It crashed into a field near Staines, killing everyone on board, in what was at the time the deadliest air disaster in British aviation history. The investigation confirmed the tail design was sound only as long as the safety system protecting it stayed active, and it triggered stricter rules worldwide governing how stall protection systems could be disabled, and by whom, including new requirements around cockpit procedures for isolating safety systems mid-flight. Quick pause here. If you're into aviation history like this, subscribe now and hit like. It genuinely helps this channel keep making videos exactly like this one. BAC-111. The Trident wasn't alone in discovering deep stall the hard way. Nearly a decade earlier, a British prototype with the same basic T-tail layout, engines mounted at the rear, tail set high above the wing's wake, was put through stall testing exactly as regulations required before the aircraft could be certified for passenger service. During one test flight in 1963, the aircraft entered a stall, and the tail lost effectiveness almost immediately, exactly the deep stall condition that would later doom the Trident nearly a decade afterward. The crew couldn't recover. The aircraft descended nearly flat, nose high, and crashed, killing the test crew on board despite their considerable experience and training. At the time, deep stall wasn't yet a well-understood phenomenon anywhere in the industry, and this crash became one of the first real-world demonstrations of it, forcing engineers to essentially learn the physics of the problem from the wreckage itself. The investigation directly shaped the requirement for stick pusher systems on T-tail aircraft going forward, meaning the very safety system that failed to save the Trident 9 years later existed largely because of what engineers learned from this earlier crash, a grim thread connecting two separate disasters nearly a decade apart. Boeing 737 Classic. Decades before Macis became a household name, an earlier generation of the same aircraft family carried a completely different hidden flaw, buried inside a single hydraulic valve controlling the rudder. The rudder power control unit could, under a narrow set of thermal and mechanical conditions involving temperature extremes and specific hydraulic fluid contamination, jam internally and then reverse itself, commanding full rudder deflection in the opposite direction from what the pilot was actually asking for, with almost no warning before it happened. In 1991, a flight approaching Colorado Springs suddenly rolled and dove into the ground, killing everyone aboard, with no clear mechanical cause found at the time, despite an extensive investigation. In 1994, a nearly identical flight near Pittsburgh rolled violently and crashed on approach, again with no obvious explanation, leaving investigators with two nearly identical tragedies and no confirmed mechanical cause connecting them. Investigators eventually recreated the failure using an incident aircraft that experienced an uncommanded rudder hardover but managed to land safely, giving engineers a rare working example of a jam that had killed two full plane loads of people without leaving useful wreckage evidence behind in either prior crash. The fix required redesigning the valve entirely and retrofitting the rudder control system across the entire global 737 fleet, one of the largest and most expensive safety modification programs in commercial aviation history at the time, affecting thousands of aircraft already in service worldwide. Airbus A300-600. Composite materials promised lighter, stronger aircraft structures, and this aircraft's tail fin and rudder were built almost entirely from carbon fiber, rather than traditional aluminum, a genuine engineering advance for its era. In November 2001, a flight departing New York encountered wake turbulence from a preceding aircraft shortly after takeoff, a routine and generally manageable occurrence for experienced crews. The first officer responded with a series of aggressive, alternating rudder inputs, motions the flight control system allowed at that speed without limiting how hard or how often the rudder could move, since the system assumed pilots wouldn't need or want to apply such extreme inputs repeatedly. The repeated side loads exceeded what the composite tail structure had ever been certified to withstand under those specific conditions, and the entire vertical fin sheared off the aircraft mid-flight in a matter of seconds. Without a tail, the aircraft became completely uncontrollable and crashed into a residential neighborhood, killing everyone aboard and several people on the ground below. The investigation revealed that pilots hadn't been adequately warned how sensitive the rudder controls were at that speed, and how easily repeated full inputs could rack up structural loads well beyond any single input's rated limit, even though no individual movement exceeded the aircraft's certified limits on its own. Training procedures for rudder use in wake turbulence recovery were rewritten across the entire industry as a direct result, specifically emphasizing that repeated aggressive inputs could be more dangerous than a single large one. ATR-72. Turboprop aircraft rely on inflatable rubber boots along the leading edge of the wing to break ice away during flight, a system that had worked reliably for decades across the industry. But this aircraft's wing design had a specific vulnerability the boots weren't built to handle. In certain icing conditions involving supercooled large droplets, larger and wetter than the ice the boots were designed around, ice could form into a ridge just behind the protected boot area, a spot the de-icing system never reached and was never designed to reach. That ridge disrupted airflow over the aileron enough to cause a sudden, uncommanded roll, an effect the crew had almost no way to anticipate or recover from once it began, since the aircraft could otherwise appear to be handling icing conditions completely normally right up until the moment it wasn't. In October 1994, a flight holding in icing conditions over Indiana rolled violently and dove into a field, killing everyone aboard in a matter of seconds. The investigation traced the failure directly to that ice ridge phenomenon, a gap between what the certification testing of the era considered and what genuinely severe icing could actually produce in real flight conditions. It led to a broader overhaul of how icing certification worked across the entire industry. Specifically targeting the kind of large droplet icing this aircraft's wing had never been tested against, and prompted new restrictions on flying certain turboprop models into similar conditions until fixes were implemented fleet-wide. Boeing 737-200. Metal fatigue didn't disappear after the comet forced the industry to take it seriously decades earlier. It just found new ways to hide inside aircraft nobody expected to age this fast. This particular aircraft, flying short, frequent island-hopping routes in Hawaii, accumulated an extraordinary number of pressurization cycles relative to its age, far more than a typical long-haul jet flying the same number of calendar years, simply because it took off and landed so many more times per day. Salt air corrosion combined with that repeated stress along the fuselage's riveted lap joints, weakening the bonded structure in ways that were extremely difficult to detect from routine visual inspection alone, hidden beneath layers of paint and structure. In April 1988, a large section of the upper fuselage tore away entirely during flight, ripping open the cabin roof at cruising altitude in an explosive decompression that stunned the entire industry. Remarkably, the crew managed to land the aircraft with a gaping hole down much of its length, an extraordinary feat of airmanship, though one flight attendant was tragically swept out and lost. The investigation forced a fundamental rethink of how aging aircraft were inspected, introducing the concept of widespread fatigue damage, cracking that develops simultaneously at multiple points across an aging structure, rather than starting from one obvious location. a pattern standard inspection techniques of the time simply weren't designed to catch, and led directly to new aging aircraft inspection programs adopted across the entire industry. McDonnell Douglas MD-80. Some catastrophic flaws hide not in the design itself, but in how a design ages under real-world maintenance decisions made years after an aircraft first enters service. The horizontal stabilizer on this aircraft is adjusted by a jack screw and nut assembly, a mechanism requiring regular lubrication to prevent the internal threads from gradually wearing away under constant mechanical load. In January 2000, a flight off the coast of California experienced a stabilizer that jammed at an extreme nose-down position, the result of a jack screw nut worn down over years to the point of catastrophic thread failure, essentially stripped smooth from years of insufficient lubrication. The crew fought the aircraft as it pitched violently, briefly regained partial control through extraordinary effort, and ultimately lost the aircraft entirely, crashing into the Pacific with no survivors. Investigators found the airline's lubrication and inspection intervals had been extended over the years, stretching the maintenance schedule further than the mechanism's actual wear tolerance could safely support, a change made for cost and scheduling reasons that nobody had adequately tested against the part's real-world wear rate. It wasn't a single design flaw so much as a slow-motion collision between an aging mechanical part and a maintenance schedule that no longer matched how quickly that part could fail, and it forced airlines across the industry to tighten stabilizer inspection requirements immediately afterward, with mandatory checks far more frequent than the interval that had been in place before the crash. Yakovlev Yak-42. The MD-80 wasn't the only aircraft brought down by a stabilizer jack screw, and this Soviet trijet suffered a chillingly similar failure over a decade earlier, triggered by an entirely different underlying cause. During a snowy 1982 departure from a Russian airbase, melted ice and moisture worked their way into the stabilizer trim system's wiring, causing a short circuit that drove the horizontal stabilizer trim motor to run uncommanded, slowly winding the tail toward a nose-down position the crew never asked for and had no immediate way to diagnose. As the aircraft climbed, the mistrimmed stabilizer fought the crew's control inputs harder and harder, and the aircraft eventually nosed over and dove into the ground, killing everyone aboard, including much of a well-known Soviet ice hockey team traveling together. Investigators traced the failure to inadequate moisture sealing around the trim system's electrical components, a vulnerability nobody had seriously tested for in the cold, wet conditions the aircraft regularly operated in throughout Soviet winters. It led to redesigned sealing and moisture protection standards for trim systems across Soviet airliner programs going forward, a quieter, far less publicized cousin of the exact mechanical failure that would later doom an MD-80 off the California coast nearly 2 decades afterward. Two very different root causes, converging on the exact same catastrophic outcome. Airbus A330. Some catastrophic flaws don't come from a single dramatic failure, but from a sensor quietly feeding pilots the wrong information at the worst possible moment, in the worst possible conditions. This aircraft's airspeed data comes from small external probes called pitot tubes, which measure air pressure to calculate how fast the aircraft is actually moving through the air. In June 2009, a flight crossing the Atlantic flew into a high-altitude storm, and ice crystals blocked all 3 pitot tubes simultaneously, a known vulnerability with that particular probe model that airlines were already in the slow process of replacing fleet-wide, though not yet on this specific aircraft. With airspeed data suddenly unreliable, the autopilot disconnected and handed control back to the crew, with almost no warning, in complete darkness, in heavy turbulence, with confusing and sometimes contradictory instrument readings flashing across the cockpit. The crew, trained on an aircraft that normally protected them from aerodynamic stalls automatically through built-in flight envelope protections, misread the situation entirely and held the nose up as the aircraft lost speed and entered a full aerodynamic stall it never recovered from, descending into the ocean over several agonizing minutes and killing everyone aboard. The investigation forced an accelerated fleet-wide replacement of the vulnerable pitot tube model well ahead of the original schedule, and a fundamental rethink of how pilots are trained to handle the sudden loss of automation at cruising altitude, a scenario the industry had quietly assumed would almost never happen given how rare simultaneous multi-probe failures were believed to be. From a tail design that could blank itself out in the wrong conditions, to a handful of blocked sensors that handed a plane back to confused pilots in the middle of a storm, every aircraft on this list carried a flaw that stayed hidden until exactly the wrong moment exposed it. If you made it this far, you clearly love this kind of deep dive, so make sure you're subscribed and drop a like before the next one drops.